Hi there, and welcome to this lesson on Pure Mathematics 3. And in this lesson, we'll be looking at how you differentiate exponential and logarithmic functions. In a previous lesson, we considered functions of the form f of x equals a to the power of x, and we noted that if a is bigger than 1, then f of x will have the form below. Doesn't matter what the value of a is, the graph will look something like that. As x increases in value, the value of y increases and the gradient increases as well. The graph gets steeper and steeper. We also saw that there is one particular value of a where both y and the gradient increase at exactly the same rate as each other. And the consequence of that is that if you choose any point whatsoever on the graph, if you find the value of y at that point and you find the gradient at that point, they're exactly the same as each other. So for instance, this intersection point here on the y-axis, the y value is 1, the gradient will also be 1 at that point. Now, this value of a, where that works, is an infinite decimal, which begins 2.71828. Like pi, it's an irrational number, it's an infinite decimal with no pattern to it, and it is given a special name, and the name is e. E is 2.71828. Now what this means is that for all real values of x, if y equals e to the x, then dy by dx is also equal to e to the power of x. So when I differentiate y, it doesn't change. Or using function language, if f of x is equal to e to the x, then f dashed of x is equal to e to the x. Now e to the x is the only function that this works for. It's the only function that does not change when you differentiate it. Using the chain rule, we can differentiate y equals e to the power of kx, where k is a constant. If y equals e to the power of kx, then dy by dx equals, first of all, you differentiate the e, and when you differentiate the e, nothing happens. It stays the same. You've got e to the power of kx. Then you differentiate the kx, and when you differentiate that, you get k. So that gives you dy by dx is equal to k e to the power of kx. Okay, 5 examples for you to have a go at. They gradually get harder as you go down through them. But have a go yourself first, pause the video, and then come back to me again when you're ready. Okay, let's have a look at these. So question 1, y equals e to the power of 5x. When I differentiate that, first of all, differentiating e, nothing changes. I just get e to the power of 5x. Then differentiating 5x, I get 5. Multiplying those together gives me 5e to the power of 5x. Second question, exactly the same idea. You've still just got a constant times x here. When I differentiate the e, I'll just get e to the power of minus 3/4 x. Then differentiating the minus 3/4 x, that gives me minus 3/4. So minus 3/4 times by e to the power of minus 3/4 x. Question 3, with a constant on the front, you're effectively using the product rule here. So I'm writing down the 7 and differentiating the e to the 4x. And when I do that, I get 7e to the 4x times by 4. And 4 sevens gives me 28 e to the power of 4x. Question 4, nothing new here. There's just 2 terms and you do both of them in exactly the same way. Differentiating this, I'll be timesing by 2, which will give me 6e to the 2x. This one you need to be a little bit more careful with. When I differentiate this, I'll be timesing by minus 1/4. Minus 1/4 times minus 4 is plus 1. So when I differentiate that, I'll get 6e to the 2x plus e to the minus 1/4 x. Fifth question is a bit more fiddly. The way into this is to split it up into 2 parts. So I've got 3 divided by 4e to the 2x, and I've got minus 2e to the 5x divided by 4e to the 2x. And I'll write those 2 parts down separately. Once I've done that, the easiest way to deal with the numbers is just keep them as a fraction, 3 over 4, and e to the 2x goes to the top and becomes e to the power of minus 2x. Same thing with the fraction here, 2 over 4, well that simplifies to a half. And using the rule for powers, 5x take away 2x gives me e to the power of 3x. Then that, I'll get 3/4 e to the power of minus 2x times by minus 2, which gives me that. And differentiating this, I'll be timesing by the 3, which gives me the minus 3 over 2 e to the 3x. This first fraction could be simplified, and that would be the final answer. Okay, what about log x, log to the base e of x? How do we differentiate that? Well, the method is we let y equal log x, and then this next step is the slightly strange one. We choose to take e to the power of y and e to the power of log x. So we do e to the power of both sides, e to the power of the left-hand side, e to the power of the right-hand side. And the reason why we do that is because e and log are inverse functions, so they cancel each other out. And the right-hand side simplifies to x. Having done that, we then differentiate both sides. Now, differentiating both sides with respect to x. The right-hand side is easy to differentiate. If you differentiate x, you just get 1. Differentiating e to the power of y with respect to x, that's more tricky. We have to use both the chain rule and implicit differentiation. When I differentiate the e, I'll just get e to the power of y. But then when I differentiate y with respect to x, that gives me dy by dx. So differentiating the e, that just gives me e to the y. Differentiating y with respect to x is just dy by dx. And as I say, the right-hand side, differentiate x, that just gives you 1. Moving the e to the y to the other side would give me that. And that simplifies to 1 over x, because up here I've said that e to the y equals x. So I've just substituted that in here. Therefore, our starting point was y equals log x, and our finishing point was, if y equals log x, then dy by dx is equal to 1 over x. So if I differentiate ln x, log to the base e of x, I get 1 divided by x. The really significant thing about that is when we do integration, because it means if I integrate 1 over x, I get ln x. And that we use in all sorts of ways when we do integration. Differentiating y equals log kx. So if I had log 2x or log 5x or log 10x, the result is quite surprising. What we do is use one of the laws of logarithms, the multiplication law, to split up log kx. And we split it up into y equals log k plus log x, just using the normal rule with logarithms there. Then we differentiate both sides. Differentiating the left-hand side gives us dy by dx. Log k is just a constant. If I differentiate a constant, I get 0. And then if I differentiate log x, we've just discovered, I get 1 over x. Now what that means is, if y equals log kx, it doesn't matter what k is, I'll always get the same answer. So if I differentiate log 2x, the answer is 1 over x. If I differentiate log 5x, then dy by dx is 1 over x. Log of minus 7x, if I differentiate it, I'll get 1 over x. It does not matter what this constant is. You always get the same answer, which is quite surprising. Okay, bearing all of that in mind, 3 examples for you to have a go at. Differentiate the following 3 functions with respect to x. Pause the video, have a go, come back to me when you're ready. Okay, let's have a look at these. So the first one, y equals log 10x. Now I could just use the rule, but what I'll do is I'll use the same method as we used to get the rule. So I can split that up into 2 parts, log 10 plus log x, and then differentiate it. When I differentiate it, log 10 is a constant, that'll give me 0. And when I differentiate log x, I get 1 over x. So, as we said, doesn't matter what the number is here, if I differentiate y, I will get 1 over x. Second example, y equals log of x squared. The way to get started on this question is to use the law of logarithms with powers. So I will rewrite that as y equals 2 log x. And then I'll use the product rule to differentiate that. So I write down the 2 and I differentiate log x. So dy by dx will just equal 2 divided by x. And the third question, y equals 3 log x to the 4 plus log 5x. I'm going to use the power rule to tidy the first term up and the multiplication rule to tidy up the second term. And that'll give me y equals 12 log x, 3 times 4 gives me the 12, plus log 5 plus log x. Then I'll do the differentiation. Or before I do that, 12 log x plus log x, I can tidy that up. That gives me y equals 13 log x plus log 5. Then I'll differentiate. And differentiating the 13 log x, same as before, write down the 13, differentiate the log x, that gives me 1 over x. And log 5 is a constant, so when I differentiate it, I get 0. And the final answer is dy by dx equals 13 divided by x. Now, the final example is a proof that you're supposed to know, but I think it's highly unlikely to turn up in the exam. And it's proving that if y equals a to the power of x, so it's not a could be any number whatsoever, then if I differentiate y, I get log a times by a to the power of x. The proof is a little bit fiddly. I'll give you some hints to get you started, and then I'll let you have a go yourself. Now, the way into this is by letting y equal e to the power of log a to the x, which is actually exactly the same as that. The e and the log are inverse functions, so they cancel each other out, and you do just have y equals a to the x. And we then use the law of logarithms to rewrite the power. So log of a to the x, we write as x log a. And then you move on from there. Now, I'll let you have a go at doing this yourself first. As I say, it is a bit fiddly, but have a go, pause the video, and then come back to me when you're ready. Okay, let's have a look. So as I said, we're starting with y equals a to the power of x, but we're choosing to rewrite that in what looks like a very complicated way, where you write it as e to the power of log a to the power of x. And as I said, they're inverse functions, so they would cancel and just leave you with y equals a to the power of x. Then we use the law of the logarithms to rewrite the power as x log a, and then we differentiate. Now, when we differentiate that, the first thing that happens is nothing, which is always the case with e. So when you differentiate the e, you just get exactly the same thing. Then we have to differentiate the power. Now, the power is log a times x, a constant times x. So when I differentiate the power, I do just get log a. Tidying that up gives dy by dx is equal to log a times by e to the power of x log a. Now, if you look up here, e to the power of x log a, well, that's the same thing as y. So I can rewrite that as dy by dx is equal to log a times by y. But if we go back to the very top, y is equal to the a to the power of x. So instead of writing y, I can just write a to the power of x. And that gives me the result that I'm trying to prove. That if y is equal to a to the power of x, then dy by dx is equal to log a times by a to the power of x. Okay, that gets us to the end of this lesson. If you've got the textbook, turn to page 127 and have a go at exercise 6b. Thank you very much for listening, and cheerio.